Hello everybody, welcome back to Glaciers and Glacial Geomorphology and the second part of our session on the basal ice layer. Last time we talked about what the basal ice layer actually is, why it matters and some of its key characteristics. Those characteristics included the high debris content, low bubble content, debris structures including tectonic or deformation structures and a specific isotopic composition. And those in combination give us some clues as to the origins of basal ice. This session, that's what we're going to come on and talk about in more detail, the origins of the basal ice layer. You'll see from this slide there's a lot of early hypotheses, if you like, lots of ideas floating around in the literature from the late 1800s and through into the middle part of the 20th century, arguing about whether shearing or folding or thrusting or freezing on of material, refreezing of water at the base of the glacier, sticking debris onto the bottom, whether those were the principal mechanisms by which basal ice was created. And there was lots of backwardsing and forwardsing and really no strong consensus as to which of these methods were even possible, let alone which ones actually happened. And a couple of key papers in there that you might want to check up on in the background reading to this would be the Vietman 1961, which is a classic paper on the possibility of freezing on of debris to the base of the glacier by the refreezing of meltwater. And he argued for the fact that shearing entrainment was relatively unlikely. But other people argued the contrary, that in fact the shearing or the thrusting in of debris from the bed was the most likely mechanism for getting debris into the basal ice layer. And I wrote a paper in 1987 in which I said that there were a plethora of theories and counter-theories, but very little in the way of critical field testing. So even as recently as 1987, people were not really sure what was going on in terms of which were the actual mechanisms for the formation of basal ice. So what I'm going to do over the next few minutes is say a little bit about these early hypotheses and how we moved on from those and began to put a little bit more certainty into our understanding of the basal ice layer, partly by virtue of stable isotope analysis. First of all, analysis in delta oxygen 18, but then further developments in stable isotope analysis using both deuterium and oxygen 18 ratios, and that co-isotopic analysis really enabled us to pin down in a little bit more detail what was going on with meltwater refreezing and the formation of ice at the bed of the glacier. But even after that, there were still unresolved issues, and I'll bring us up to date by identifying some of those remaining uncertainties and controversies in the origin of basal ice. And we'll have a follow-up session, a further video, which just pulls out that last little bit of what I'm talking about today and explores that as a case study, looking at glaciohydraulic supercooling as one possible explanation for some of the basal ice that we can find in some glaciers in different parts of the world. So you're familiar already with this diagram from Lawson 1979, where he's showing the stratigraphy through the Matanuska Glacier from the surface, through the englacial facies, through to the basal ice layer. But what we didn't spend much time last time talking about was this additional diagram, which is showing the stable isotope profile through the bottom part of the englacial facies and across the border, across the boundary into the basal ice layer, the dispersed facies and the stratified facies. I'd just like to explain in a little bit more detail what we can infer from this stable isotope pattern with the steadily decreasing delta oxygen 18 value with depth through the englacial facies, then the sudden step to the right that you're seeing in the isotope signature as we move down into the stratified facies. What could explain that? And you can see in the diagram there that we're going from about minus 24 per mil delta oxygen 18 back up to about minus 21 per mil, so a step to the right, or a move to the right of about 3 parts per mil in the delta oxygen 18 value. What could explain that, and how might that help us to understand what's happening in the basal ice layer? Let's think first of all about the steady decrease in isotope values down through the englacial facies. Well, we're familiar with that. We would understand that already from what we've talked about in previous sessions. If you drill down through an ice sheet, through a glacier, and you sample stable isotope values, or we sample the ice and take stable isotope values through the thickness of the englacial facies, what are you actually sampling? Well, if you're not right at the summit of an ice sheet, then what you're sampling is ice at greater and greater depths, which has come from different locations up glacier. Put that into context. Here's our whole ice sheet model. Here's the flow pattern through the ice sheet, and I've drilled an ice core through there. So near the top of the ice, we're looking at relatively locally sourced, low elevation ice. The further down we go, we're looking at ice which has come from closer and closer to the centre of the ice sheet, from higher and higher elevations, colder and colder locations, theoretically further and further from the ocean. So you would expect to get isotopically progressively more negative snow falling and ice forming at those different layers on the ice sheet. So you would expect a graph of delta oxygen 18 against depth to show a gradual trend to more negative values as you go down through the column. So on Lawson's diagram there, it's no surprise at all that at the bottom of the end glacial facies we have a line sloping a little bit like that. But then the line zips off to the right and does different stuff by about 3 parts per mil at the top of the stratified facies basal ice layer. What might be happening there? Well, here's one theory to explain that. Imagine at the base of the glacier, so here's the ice, here's a substrate. Imagine we have melting at the base of the glacier. Now, melting doesn't involve any isotopic fractionation, so the meltwater flowing at the base of the glacier here is going to have an isotopic composition derived from the isotopic composition of that ice which is melting to generate the meltwater. Suppose then, as we move towards the edge of the glacier, the basal thermal regime changes, either the pressure regime or the actual temperature changes, and we start refreezing that meltwater onto the bed of the glacier. But we don't refreeze all of the meltwater. We refreeze some of the meltwater, but we allow some of the meltwater to escape, or if you're on a deformable or a permeable substrate, maybe some of the meltwater escapes into the substrate. If you're on a rigid substrate, then maybe some of the meltwater escapes from the glacier, or certainly escapes from our local area that we're examining here to consider the formation of basal ice here by the refreezing of that meltwater. Now, you know from previous sessions that if you evaporate, or if you condense and precipitate, or if you freeze water, that freezing involves an isotopic fractionation. So if you started with a bucket of standard mean ocean water and you started freezing layer by layer, remember we did this previously in one of the previous lectures, then you would anticipate that the heavier isotopes would tend to get caught up first in the frozen fraction, and the lighter isotopes, the oxygen 16s, if we're looking at 16-18 ratios, would tend preferentially to escape that freezing front and remain in the parent liquid. So if we imagine that happening here at the base of the glacier, well, that's exactly what we'd expect to happen, that you'd preferentially trap the heavier isotopes into these refreezing meltwaters that are generating ice, whereas the lighter fraction preferentially would escape in the meltwater. So you'd have an isotopically light meltwater and an isotopically heavy or positive refrozen ice layer. If you go through the theory of that and look at the physics of that, the amount of fractionation or the amount of isotopic enrichment that you would expect in that basal ice layer would be about 3 parts per thousand. In other words, it very much matches what we showed you previously, the diagram from Lawson, with that 3 parts per mil step to the right as you go down into the basal ice layer. So this suggests and supports the hypothesis that the basal ice layer, the stratified facies of the basal ice layer, because it shows that 3 parts per thousand enrichment in the delta oxygen 18 values, well, that's consistent with it being refrozen from meltwater at the glacier bed. It's a good hypothesis at this stage, but ideally we'd have some more evidence that would really enable us to pin that down. So what we've done so far is just by looking at the one isotope ratio, the oxygen 18 to 16. What comes next in the story is looking at two isotope ratios and comparing them, the oxygen 16 to 18, but also the deuterium to hydrogen. So doing for the hydrogen ratios the same as what we've just done for the oxygen ratios. And that's a big step forward in stable isotope glaciology as it applies to understanding the basal ice layer. So if you want to do some reading on co-isotopic analysis, there's lots of stuff out there for you to have a look at. This slide shows some of the key early papers that you should refer back to, the Giselle and Souchet and Giselle, and also a couple of case studies, the Sugden et al. Relating back to some work that people now at Kiel were doing, and that more recent examples from Goossens et al. 2016 that I referred you to earlier on. And in the picture here, that's Reggie Lorraine, Dave Sugden and Roland Souchet in Greenland actually doing some co-isotopic analysis that led to what they're talking about in that Sugden et al. 1987 paper. Now, the basis of co-isotopic analysis is that as well as measuring variations in the delta oxygen 18 values, so oxygen 18, oxygen 16 ratios, we also measure variations in the hydrogen, i.e. the H1, the hydrogen, and the H2, the deuterium. And then we compare what's happening with the fractionation in the oxygen with what's happening in the fractionation in the deuterium. And what Giselle, Souchet and others came up with was the idea that as we go through that same thing we were talking about before, gradually freezing, frozen fraction 1, frozen fraction 2, frozen fraction 3, remaining parent water, so we're freezing our bucket of water that maybe starts off as standard mean ocean water, so a fixed standard isotope value to begin with. The frozen fractions will be initially enriched in the heavier isotope relative to the parent water, making the parent water relatively depleted in the heavier isotope. And so they plot these values for the different freezing fractions on a graph that has the delta oxygen 18 value on that axis and the delta deuterium value on that axis, moving negative in that direction, negative in that direction with our 0 point up there, and any positive values up in these directions. So for freezing, if we were to start with a parent water that was standard mean ocean water, our first frozen fractions would be up here somewhere with positive values, but then as we essentially use up a lot of our stock of the heavier isotopes, as we move further and further down, freezing more and more of this, getting into the last sections of the reservoir for us to freeze, this obviously stops being standard mean ocean water because we're fractionating the heavier isotopes and leaving the lighter isotopes behind. And so these final fractions would plot out down here somewhere on our graph. And what Giselle, Souchet and others found was that, well, if you plot those samples on our graph, they come out with a predictable, what we call freezing slope. And there's a particular equation for that freezing slope related to the fractionation coefficients of the hydrogen and the oxygen. The important point here is that we can compare the freezing slope with the precipitation slope, or the meteoric waterline, which is the isotopic signature that you would expect for snow and therefore what you would expect for glacier ice. If we were to plot the meteoric waterline onto here, so all the world's snowflakes, all the world's raindrops, all the world's end glacial glacier ice facies, all of those samples should lie on a line with a particular equation, delta D equals roughly 8 times the delta oxygen 18 value plus about 10. So in other words, for any value of oxygen 18 that you might choose, if it's meteoric water, it's going to lie on this meteoric water line, so the delta deuterium value you'd expect, you'd predict, you'd associate with the meteoric water line is going to be 8 times the delta oxygen 18 value plus 10. So if delta oxygen 18 had a value of minus 10 per mil, then if it's a meteoric water line, the delta deuterium value would be 8 of that, so minus 80 plus 10 minus 70 parts per mil. and the meteoric waterline will plot out on that. And so if the delta oxygen 18 value is 0, then the delta deuterium value would be 8 times 0 plus 10. And that's why the meteoric waterline intercepts with the axis just above the 0 point there. Suchet, Giselle and others came up with a formula that can give you S, the slope, the gradient if you like, so this has a gradient of 8. They came up with the equation that's in your reading, for the equation that gives you the gradient of the freezing slope. And the key point is that the gradient of the freezing slope is different from the meteoric waterline, and it can be predicted for different parent waters. So the freezing slope is a function of the parent water that you take to freeze. Let's clean the board up a little bit. So I've drawn on the meteoric waterline. The important thing, or one of the important things about the Giselle and Suchet formula is that for different parent waters that you might find from different positions on this meteoric waterline, so for example a parent water from a glacier in Iceland, or a parent water from a glacier in Antarctica, which is likely to have much more negative values, the calculated freezing slope that you would expect to get if you melted that, put it into a bucket, froze it layer by layer, sampled the layers, and then plotted those samples out onto this graph, the freezing slopes at those different levels would be different. And you could work back from that slope or that slope to figure out what the parent water must have been if it was on the meteoric waterline. So if it was end-glacial fasces ice, which would lie on the meteoric waterline, other things being equal because it's formed from snow that falls at the glacier surface, if you sample your refrozen water, run up that slope on the assumption it came from meteoric water, you can identify what the parent water must have been that was frozen to create your refrozen ice. So not only can you recognise that it is refrozen ice rather than meteoric ice, but you can also identify what the water was that must have frozen to generate that ice. That's a really powerful tool in glaciology, using this co-isotopic analysis. So it's a really powerful tool in glaciology and has a lot of different applications. For example, telling whether ice is meteoric ice, fell out of the sky as snow to form a glacier, or if it's refrozen, if it's melted and then refrozen again. If you have got refrozen ice units, for example, ice in the basal ice layer of a glacier which is refrozen from meltwater, then you can use co-isotopic analysis to identify what the source water for that refreezing was. And so if you have a number of different ice units within a glacier, you can use co-isotopic analysis to differentiate ice of different provenances. You can see where different bodies of ice within a glacier actually originated in terms of their source, either as meteoric ice or as from meltwater of different types. Or if rainwater got into the system, for example, you can reconstruct the parent waters for refreezing events. So on the basis of using co-isotopic analysis in that way and combining it with our previous understanding of freezing on, shearing and other processes within the basal ice, I'm going to kind of fast forward a little bit and bring us to a point where we can present a very simple model of the major processes of basal ice formation, and kind of around about the late 1980s and into the 1990s, this is where we were with our understanding of the basal ice layer, and we said, for a simple model of basal ice formation, would say the stratified fasces, well, that seems to be formed by freezing on. And that information you saw from the isotope values that Lawson showed up for the Matanuska Glacier, they were consistent with that, and they were subsequently backed up with co-isotopic analysis of ice from other locations around the world, indicating that stratified fasces was very much associated with basal freeze-on. The debris bands appear to be a combination of basal freeze-on to actually get the debris into the ice, but then tectonic processes, stacking, by deformation within the ice to generate the thick sequences. So it isn't a case of either or the basal freeze-on and the shearing and thrusting. It's both basal freeze-on and shearing and thrusting to generate the stratified facies and the debris bands that are, in a sense, structural extensions of the stratified facies or structural extensions of the thin frozen layer at the glacier bed. The dispersed facies that we talked about previously, that's turned out to be a little bit more complicated, and that's still a little bit controversial, but a number of theories are out there that focus around the dispersed facies being a kind of metamorphic alteration of glacier ice. So it isn't straightforward unaltered glacier ice, it has experienced some kind of changes going on, but it isn't simply refrozen from meltwater at the bed, or so it would appear. The jury's still out a little bit on the dispersed facies, so keep your eyes on the current literature and the recent literature to see what's going on with that. And that's kind of been the story throughout, that you need to keep your eyes on the literature to know what's going on with basal ice, because the ideas have been changing over the course of time. That's one of the things that makes it so interesting, so exciting. And one of the problems with this simple model is that glaciologists like me were wandering around temperate and subpolar glaciers saying, whoa, look at this fantastic thick basal ice sequence. Yeah, that's formed by freezing on of meltwater at the glacier bed, blithely ignoring the fact that we were at a temperate glacier where you really expect there to be melting at the bed. And if there's melting at the bed, well, how are you generating this thick sequence of frozen on debris? You could understand it in Greenland, for example, where there's a cold fringe and meltwater from the interior is freezing when it reaches the edge of the glacier. But in somewhere like Iceland, for example, or Alaska, you don't really have that cold marginal environment to explain so much freezing on as you'd really need to generate the thickness of basal ice that we see in lots of different locations. So a new hypothesis that emerged is this idea of subglacial glaciohydraulic supercooling, which is a bit of a mouthful, but it's an important mechanism for you to be aware of. So the idea of subglacial glaciohydraulic supercooling is that as ice moves through the glacier to the margin, in many situations it moves through what we call a subglacial overdeepening. Now, if you remember what we've talked about previously in terms of where the shear stress is greatest, where the erosion is likely to be greatest underneath the glacier, and you realise that the shear stress and the glacier velocity and the glacier thickness all diminish very quickly right close to the margin, so you would predict a zone of greater erosion a little bit in from the margin, but not way up in the deep interior of the glacier. We'll talk about this again when we talk about glacial geomorphology. But it turns out that for a lot of glaciers there is an over-deepening a little way inland from the glacier margin, and meltwater from the interior makes its way through this over-deepening. Now, at the bottom of the over-deepening, it's at high pressure because of the overburden pressure of the ice, and as it emerges under hydraulic pressure from the interior of the glacier, as it emerges from that over-deepening up to the edge of the glacier, the pressure, the overburden pressure, releases quite quickly because the slope of the bed is rising and the slope of the glacier is diminishing as well. So the rate of thinning of overburden is sufficient that this water, which was liquid at the pressure underneath the thickest bit of the glacier, suddenly finds itself now at a much lower pressure, and it needs to, its melting point needs to adjust because it may be below zero, below the atmospheric pressure melting point, because it was at a higher pressure. The pressure now diminishes, so essentially the water finds itself below its new freezing point as it emerges at the edge of the glacier into this much lower pressure environment. So it's emerging into the low pressure environment below the freezing point, but still liquid. That's supercooled. So now out in the atmosphere, it freezes. And so ice rising up this adverse slope is freezing as it goes because it's finding itself becoming supercooled because of the change in pressure. So without having a really cold ice marginal environment, this change in pressure generated by the subglacial morphology could be enough to create stratified facies basal ice by this supercooling process. That's the theory. Now, when that theory emerged through the 1990s and up to around about the year 2000, some people thought, well, this is the bee's knees, this is fantastic, this solves all our problems. In fact, given that you can create basal ice by glacier hydraulic supercooling, well then that must be how basal ice is created. And for a while a number of people were saying, wow, yeah, supercooling explains all of basal ice formation. Other people, and you can see in the slide on the right here, the Spedding and Evans in Sedimentary Geology actually put in their paper a reference to the fact that referees for the paper were encouraging them to come out and agree that, yeah, supercooling is the way forward for this. But their expression there, referees urge us to accept that glacier hydraulic supercooling accounts for the extensive layers of basal ice. We believe that such certainty is premature. Now that's a nice line for most types of science. Certainty is premature. That's a good code to go by for a lot of things. So that's a really important issue there. Supercooling, really important process, probably generates a lot of basal ice in situations where you otherwise wouldn't create it. But are we generating all the basal ice by that mechanism, or are there other mechanisms also going on? Now I'm going to put together a separate video for you, looking in a bit more detail at some of the research that went on around subglacial glacier hydraulic supercooling, and I'll give you my personal take, if you like, based on some research as to where we are with that area of understanding the basal ice layer. But for now, I'll just leave you with these kind of conclusions of that research. We'll come back later and we'll look at these in more detail. So I'm happy to certainly support the work that a lot of people have done, finding that glacier hydraulic supercooling is a really important way of forming basal ice in some locations. However, there are other situations where supercooling isn't the explanation, and so it isn't therefore the only explanation of basal ice. I'll also say something in this extra video that I'll produce for you about how we can use lab experiments in conjunction with field work to move forward in this area. And it's an area of research which is actually appropriate and relevant for undergraduate and for master's or PhD level study. So if any of you are interested in carrying on with your glaciers after you finish your undergraduate program, that's an area where we've been doing some work at Keele that you could involve yourself with if you wished. So anyway, that brings us to the end of these brief introductory sessions on basal ice. So I'll give you a bit of a case study session on the supercooling later on, and there's plenty of reading for you to do. But by way of conclusion to these introductory bits, I'd give you these points just to think about. Basal ice is a distinctive layer in some glaciers, not all glaciers, but in a lot of glaciers. Our understanding of it has improved partly because of techniques that have become available to us, such as co-isotopic analysis, and that's a nice case study, if you like, of how developments in the subject can lead to developments in understanding. Different basal ice facies are related to particular subglacial environments, and that means we can reconstruct what's going underneath the glacier by looking at the basal ice exposed at the margin. We can use basal ice to figure out interior conditions. Now this is relevant both to ice dynamics. Said previously, the way that glaciers move is going to depend partly on what's happening in their basal ice layer. It's also important to glacier geomorphology. The way that the glacier is going to affect its landscape is going to depend partly on what's happening in the basal ice layer, both in terms of the creation of the basal ice layer and also in terms of the basal ice layer being a sediment transfer mechanism. And one of the most important conclusions from what we've just been saying is that the origin and the distribution and the characteristics of basal ice are very much controlled by the basal thermal regime, temperature conditions at the base of the glacier, where the melting is occurring, where the meltwater is refreezing, and so on. So that means that one of the things we need to talk about next, in order to completely understand how the basal ice is working and the implications of how the basal ice is working, we need to look at the thermal regime of glaciers, the temperature of glaciers, and in particular the basal thermal regime and the geography of the basal thermal regime. So that's a topic that we'll come on to over the next few sessions.